Imagine drifting through the quiet darkness of space, far from any planet, far from the warmth of any Sunday. All around you, stars shine gently, their light taking years to reach you. And then, ahead, you see something stranger than anything you have ever known. A place where the stars bend, light curves, and even time itself seems to slow. You are approaching a black hole. What exactly are black holes? And how can some be so small they could hide inside a mountain, while others are so vast they could swallow entire galaxies? Black holes are regions in space where gravity is so strong that nothing can escape. Not light, not matter, not even time as we know it. They are born from the deaths of massive stars, but some grow to monstrous sizes, becoming cosmic giants that shape the very galaxies they live in. Tonight, we will take a long, slow journey, from the smallest black holes to the largest, from the quiet wanderers to the giants that blaze at the hearts of galaxies. We will drift close enough to see their beauty and their danger, yet always remain at a safe, peaceful distance. And as we travel, we will understand not just what black holes are, but how they live, grow, and one day fade away. So close your eyes, let your breathing slow, and join me on this journey. From tiny black holes to the giants that can eat galaxies. Out in the vastness of the universe, where silence stretches farther than any horizon and the stars are scattered like grains of light on an endless canvas, there exist objects so strange that they seem more like dreams than reality. These are black holes, not planets, not stars, not even solid bodies, but regions where gravity has become so strong that escape is impossible. Gravity is the force that pulls objects toward one another. On Earth, it keeps our feet on the ground. It holds the moon in orbit around our planet and keeps the planets moving around the sun. But imagine gravity so intense that it pulls on everything, even light itself, with such strength that nothing can break free. That is what defines a black hole. A black hole does not have a solid surface. It has a boundary called the event horizon. This is the point of no return. Anything crossing this invisible line is gone forever, pulled inward toward the center. Inside lies the singularity, a point where the mass of the black hole is concentrated into an infinitely small space. Physics as we know it breaks down there. Time and space themselves become warped in ways we cannot yet fully understand. Despite their name, black holes are not truly empty. They are packed with matter, the remains of stars, clouds of gas, or anything else they have consumed, all crushed together under unimaginable pressure. Because they do not emit light, we cannot see them directly. We only know they are there because of how they affect their surroundings. They might pull on nearby stars, cause gas to swirl in glowing spirals before vanishing, or bend the path of light from distant objects. For centuries, black holes were only an idea, a possibility suggested by mathematics. The concept first appeared in the 18th century, when a few scientists imagined a star so dense that its gravity could trap light. But it wasn't until the 20th century, when Albert Einstein's theory of general relativity reshaped our understanding of gravity, that the idea of black holes truly took form. Even then, many thought they might only exist on paper as theoretical curiosities. Today, we know they are real. We have seen their shadows against the glowing light of nearby matter. We have measured the waves they send through space when they collide. We have watched stars whip around invisible points, pulled by forces stronger than anything else in the universe. And yet, black holes remain deeply mysterious. They come in different sizes. Some are small, only a few times heavier than our sun. Others are so massive that they contain the weight of billions of suns, crushing it all into a point no larger than the orbit of Mercury. Between these extremes are the rarer, middle-sized black holes, which are harder to find and study. The smallest are called stellar mass black holes, born when massive stars run out of fuel and collapse under their own gravity. The largest are supermassive black holes, found at the centers of galaxies, including our own Milky Way. How these giants form is still a mystery, whether they grew slowly over billions of years by feeding on gas and stars, or whether they were born already massive in the early universe. One thing is certain, black holes are not just destroyers. They are also creators. Their gravity can shape galaxies, trigger the birth of new stars, and influence the flow of matter across light years of space. Without them, the universe might look very different. For us, they are both a challenge and an inspiration. They push the limits of what we can know, forcing us to imagine places where time slows, space folds, and the familiar laws of nature may no longer apply. They remind us that the universe is far bigger, stranger, and more beautiful than we can ever fully understand. And so, our journey begins here with the idea of the black hole, a place where the ordinary rules of existence end, and something entirely different begins. From here, we will move deeper, exploring how these objects are born, how they live, and how they grow from tiny points of darkness into giants that can shape entire galaxies. Every black hole begins as something far more familiar, a star. Stars are not eternal. They are born, they live for millions or billions of years, and eventually they die. But for some, death is not a quiet fading. For the largest stars, the end of life is a spectacular and violent transformation, one that can leave behind a black hole. To understand this, imagine a star as a giant balancing act. A star shines because deep in its core, hydrogen atoms fuse together to form helium. This fusion releases enormous amounts of energy, which pushes outward, counteracting the force of gravity pulling everything inward. For as long as the star has fuel to burn, this balance holds, pressure pushing out, gravity pulling in. But even the brightest stars eventually run out of fuel. When that happens, gravity wins. The star's outer layers may collapse inward or explode outward, depending on its size. For smaller stars like our Sun, the end is relatively gentle. They swell into red giants, shed their outer layers, and leave behind a white dwarf. But for the truly massive stars, those at least 8 times heavier than the Sun, the ending is far more dramatic. When such a massive star burns through its nuclear fuel, its core can no longer resist gravity. The outer layers crash inward at incredible speeds, triggering a colossal explosion called a supernova. For a brief time, this dying star can outshine an entire galaxy. The light and energy it releases in those final moments are so intense that they can be seen across millions of light years. But the supernova is not the end of the story. Deep in the star's core, gravity continues its relentless work. The matter there is crushed tighter and tighter, the pressure growing so extreme that atoms themselves are torn apart. Protons and electrons fuse into neutrons, creating an incredibly dense object known as a neutron star. Yet sometimes, even a neutron star is not the final stage. If the original star was massive enough, far beyond the threshold, its core continues to collapse. The density becomes infinite, the volume shrinks to almost nothing, and a black hole is born. Around it forms the event horizon, the invisible boundary beyond which nothing can return. The birth of a black hole is not just the end of a star's life, but the creation of something entirely new. A region of space where gravity has become absolute, where matter and light are trapped forever. In that moment, the star's identity as a glowing object is erased, replaced by a silent, invisible presence. Not all black holes form from supernovae. In some rare cases, a massive star may collapse directly into a black hole without a visible explosion. The star simply vanishes from sight, its light extinguished in an instant. Astronomers suspect this may happen when the star's gravity is so overwhelming that even the blast of a supernova cannot overcome it. And then there are the mergers. 2 neutron stars colliding can also form a black hole. When this happens, the collision sends ripples through spacetime itself called gravitational waves, which we can detect here on Earth. These waves carry the signature of the black hole's birth, allowing us to study events happening billions of light years away. Over time, a newborn black hole may begin to grow. If it is in a dense region of space, it can feed on gas, dust, and even entire stars that wander too close. This feeding process can make it brighter, not because the black hole itself shines, but because the matter around it is heated to incredible temperatures as it spirals in. This is the beginning of an accretion disk, the glowing ring of gas that sometimes surrounds active black holes. It's strange to think that something so dark can be born from something so bright. A star, after all, is a beacon, a warm, steady presence that can shine for billions of years. And yet, in the end, its death can create one of the most mysterious and powerful objects in the universe. For now, imagine watching such a transformation from a safe distance. You see a star vast, brilliant, burning with a steady light. Then, one day, its light begins to change. It swells, brightens, and then, in a sudden, blinding flash, explodes into a supernova. For weeks, it burns brighter than an entire galaxy. And then, slowly, the light fades. In its place, there is nothing visible. But something remains, silent, invisible, and infinitely heavy. A black hole. This cycle, birth, life, death, and transformation, is one of the universe's oldest rhythms. It has happened countless times, and will continue for as long as there are massive stars. In this way, black holes are not only destroyers but also part of the cosmic life cycle. Without them, the story of the universe would be incomplete. When most people imagine a black hole, they often picture something enormous, a giant, galaxy-swallowing monster. But not all black holes are giants. Some are small enough to hide inside a single mountain on Earth, yet still contain the mass of several suns. These are called stellar mass black holes, the smallest type we know of, born from the collapse of massive stars. Despite their size, they are powerful. A stellar mass black hole might be just 10 or 20 kilometers across, about the size of a city, but it can weigh as much as 10, 20, or even 100 suns. Imagine squeezing that much mass into something so compact. The result is gravity so strong that nothing can escape once it crosses the event horizon. These small black holes are scattered across the galaxy like quiet travelers. They are far more common than the giant ones at galactic centers, but most are invisible, wandering through space without any light to betray their presence. The only way we know they're there is by the way they affect the things around them. Sometimes, a stellar mass black hole has a companion, a nearby star bound to it by gravity. In these cases, the black hole's presence can reveal itself. If it pulls matter from its companion, the gas spirals inward, forming an accretion disk. This disk glows brightly in X-rays as the gas heats up to millions of degrees before disappearing into the black hole. Telescopes sensitive to X-ray light can spot these glowing disks, allowing us to find otherwise invisible black holes. One of the most famous examples is Cygnus X1, a stellar mass black hole about 6,000 light-years from Earth. It is locked in a dance with a massive blue star, stealing some of its gas and creating a bright X-ray source. For decades, Cygnus X1 has been one of the strongest pieces of evidence that black holes really exist. But not all stellar mass black holes have companions. Many travel alone through the galaxy, silent and unseen. These rogue black holes drift endlessly, remnants of stars that exploded long ago. If one passed near our solar system, though the chances are extremely small, it could disturb the orbits of planets and comets with its gravity, all without being visible. Astronomers believe there could be millions of these small black holes in the Milky Way alone. Each one is a relic of a massive star's death, a quiet marker of the violent past that shaped our galaxy. Some may be only a few million years old, newly formed from recent supernovae, while others could have existed since the early days of the Milky Way. Because of their small size, stellar mass black holes have a limited reach compared to their giant cousins. Their gravity is intense, but it only dominates nearby space. If you could somehow observe one from a safe distance, many times farther than its event horizon, it would look like an ordinary starless point in space. You would only notice its effects if you saw matter falling in, or if it passed close enough to bend the light of a star behind it, an effect known as gravitational lensing. The life of a stellar mass black hole is simple. It travels through space, waiting for chance encounters with stars, gas clouds, or anything else that wanders into its path. Over time, it may grow by feeding on what it captures, but many remain roughly the same size for billions of years, drifting in solitude. It's humbling to think that some of these small black holes might be passing silently through the galaxy right now, perhaps only a few light-years away, completely unnoticed. They do not announce themselves. They do not glow. They simply move, carried by the great spiral currents of the Milky Way. And yet, these smallest black holes are the seeds from which larger ones can grow. If they find enough matter to feed on, or if they merge with other black holes, they can slowly increase their mass. Over cosmic time, they could become intermediate black holes, and perhaps even supermassive giants. For now, picture one of these travelers. Small by cosmic standards, invisible to the eye, yet heavy enough to anchor entire solar systems in its grip. It glides silently through the dark, the faint starlight of the galaxy reflecting off the gases it occasionally pulls in. Most of the time, it remains hidden, just another shadow in the infinite sea of space. Stellar mass black holes remind us that size is not the only measure of power. Even the smallest of them can outmatch anything else in the universe for sheer gravitational strength. They are proof that the universe hides its greatest forces in the smallest, quietest packages. For much of their existence, black holes are invisible. They make no sound, give off no light, and drift silently through space. But when the right conditions arise, when gas, dust, or even an entire star wanders too close, a black hole awakens. This is when it begins to feed, and in doing so, creates one of the most brilliant and beautiful sights in the universe, the accretion disk. The process begins quietly. Imagine a star orbiting a black hole, too far away to be in danger. Over time, the balance shifts. Perhaps the star ages and swells into a red giant, or perhaps another star's gravity nudges it closer. Gas from the outer layers of the star begins to drift toward the black hole. This gas is not simply swallowed whole. Instead, it starts to spiral inward, pulled by gravity but also moving sideways because of its original orbit. The result is a wide, flat ring of matter swirling around the black hole, the accretion disk. It is not a solid surface, but a fluid, constantly moving flow of particles, gas, and dust. As the material spirals closer to the event horizon, it moves faster and faster, colliding with other particles, creating immense friction. This friction heats the disk to extraordinary temperatures, millions of degrees in some cases. And here is the paradox. The black hole itself is dark, but the accretion disk glows brilliantly. At these extreme temperatures, the inner regions of the disk emit X-rays and ultraviolet light, while the outer regions shine invisible light. Seen from a distance, an active black hole surrounded by an accretion disk can outshine entire galaxies. If the black hole is feeding rapidly, the disk can grow bright enough to be seen billions of light-years away. These blazing beacons are sometimes called quasars when the feeding black hole is a supermassive one at the center of a galaxy. But even small stellar mass black holes can produce spectacular displays when they feed. The view near the disk is like nothing else in nature. The light is distorted by the black hole's gravity, bending around it so that you can see parts of the disk that would normally be hidden. If you could look from the side, you would see the upper and lower surfaces of the disk curving up toward you, wrapped by the invisible warping of space-time itself. Sometimes, as the black hole feeds, the disk produces powerful jets, narrow streams of particles shot out from the poles of the black hole at nearly the speed of light. These jets are not matter escaping from inside the black hole. Rather, they are particles from the disk accelerated by intense magnetic fields before crossing the event horizon. They can stretch for thousands of light-years, lighting up vast regions of space. The feeding process can last for thousands or millions of years, depending on the supply of material. Eventually, the black hole may consume all the matter in its reach, and the disk will fade. The black hole will go quiet again, returning to its invisible state until new material falls into its grasp. There is a strange beauty in this process. The black hole itself is the ultimate trap, yet the path to it, the accretion disk, is one of the brightest and most energetic places in the universe. The light we see from these disks is the final cry of matter before it is lost forever. From a safe orbit, far outside the event horizon, you could watch the dance of the disk in perfect silence. The colors would shift depending on your view. Blues and whites near the hot inner edge, deep reds and golds toward the cooler outer edge. And always, at the center, the perfect darkness where the black hole waits. Even though feeding black holes are rare compared to the silent wanderers, they are vital to our understanding of the universe. The light from their accretion disks carries information about gravity, energy, and the bending of space-time, clues that help scientists test the limits of physics itself. And so, while the image of a black hole is one of darkness, the truth is that some of the brightest lights in the universe are found at their edges. The accretion disk is a paradox made real. Beauty born from destruction, brilliance shining from the brink of nothingness. Not every black hole sits in a galaxy's bustling center. Not all are surrounded by glowing disks of gas, drawing in matter with a brilliant show of light. In fact, most black holes are not feeding at all. They are silent, hidden, and alone, wandering through space with nothing to mark their presence except their gravity. These are the rogue black holes, the quiet travelers of the universe. A rogue black hole can be born in many ways. Some form when a massive star explodes in a supernova and the force of the blast kicks the newborn black hole away from its birthplace, sending it drifting through the galaxy at hundreds of kilometers per second. Others may have once been part of a binary system, orbiting another star. If that companion star dies or is pulled away by another gravitational encounter, the black hole is left to wander on its own. Once alone, a rogue black hole moves through the galaxy like a shadow, silent and invisible. Without nearby matter to feed on, it produces no light. You could pass within a few million kilometers of one and never know it, unless you could feel the immense tug of its gravity. And yet, these solitary travelers are far from rare. Astronomers believe there could be millions of rogue black holes in the Milky Way alone, drifting through the spiral arms and quiet outer reaches of our galaxy. They are relics of stars long gone, their lives as stars erased, their new lives as black holes stretching on for billions of years. Every now and then, a rogue black hole's path might take it near a cloud of interstellar gas. If that happens, it may feed a little, pulling in a small amount of material and briefly giving off X-rays or faint bursts of light. But most of the time, these black holes pass through space without disturbing much at all. The only way we can detect such an invisible traveler is by watching how it affects the space around it. If a rogue black hole passes in front of a distant star, its gravity bends and magnifies the star's light, an effect known as gravitational microlensing. For a few days or weeks, the star may appear slightly brighter, its light bent toward us by the unseen object passing between. When the event is over, the black hole moves on, leaving no trace except the measurements we were lucky enough to capture. Some rogue black holes may roam far from the galaxy's core, drifting into the quiet, thinly populated regions between spiral arms. Others may linger near star clusters, passing silently through regions where new stars are forming. In either case, their journeys are slow and steady. With no friction, no air, and almost no obstacles in space, a rogue black hole can keep moving in the same direction forever, unless another massive object changes its course. It's an eerie thought that somewhere, perhaps not too far from our solar system, a rogue black hole could be drifting right now. The distances between stars are so great that the chances of one passing close to us are extremely small. But if it ever did, its gravity could tug at comets in the outer reaches of our solar system, or bend the paths of planets in subtle ways. It wouldn't be the drama of a science fiction story, but the quiet, powerful reshaping of orbits over centuries or millennia. In the vast stillness of space, these lone wanderers are reminders that the universe is filled with motion even where nothing seems to be happening. Stars orbit galaxies, galaxies drift toward each other, and black holes, even the invisible ones, are part of this great, slow dance. If you could follow a rogue black hole on its endless journey, you would see it pass through regions of faint starlight, slip between nebulae glowing in the distance, and glide across the emptiest stretches of interstellar dark. It would never hurry, never tire, never age in any way we can measure. It would simply move always onward, carrying the weight of its past life as a star. Though they do not blaze like quasars or roar with jets of particles, rogue black holes are no less fascinating. They are the quiet side of the black hole story, the silent, hidden travelers that fill the spaces between the universe's more dramatic scenes. Between the smallest stellar mass black holes and the colossal giants that sit at the centers of galaxies, there may exist a rare and elusive class, intermediate black holes. These mysterious objects would weigh anywhere from a few hundred to a few 100,000 times the mass of our Sun, making them far larger than the remnants of collapsed stars, but still far smaller than the supermassive black holes that dominate galactic cores. And yet, despite years of searching, these middleweights are among the hardest to find. We have hints, possibilities, and a few promising candidates, But the truth is that intermediate black holes remain one of the great missing links in our understanding of the universe. If they do exist in large numbers, they could help explain how the biggest black holes in the universe were able to grow so massive. The search for them begins with a simple question. Where would you hide if you were a black hole of this size? The answer seems to be far from the crowded centers of galaxies, perhaps in dense star clusters or the faint halos of smaller galaxies. One possible home for these rare black holes is inside globular clusters, tightly packed spheres of ancient stars that orbit around larger galaxies. These clusters have existed for billions of years, and their dense cores might be perfect places for black holes to grow quietly by merging with others or feeding on nearby matter. Astronomers have spotted unusual movements of stars in some globular clusters that suggest an unseen object, possibly an intermediate black hole, is tugging on them with its gravity. Another possible home is in dwarf galaxies, small, faint galaxies that orbit larger ones like companions. In some dwarf galaxies, astronomers have found evidence of black holes that are too large to be stellar mass, yet too small to be supermassive. These discoveries are rare, but they may be the best clues we have that intermediate black holes are out there. Finding them is difficult because they rarely feed in a way that produces enough light for us to see. Without a bright accretion disk or the gravitational chaos of a crowded core, they remain quiet and hidden. The few times we think we've spotted one, it's often because a star or cloud of gas wandered too close, creating a brief flare of X-rays before vanishing into darkness again. One of the best-known candidates is an object in the galaxy Messier 82, called M82X1. It shines in X-rays in a way that suggests it is far more massive than any stellar black hole we've confirmed, perhaps around 400 times the Sun's mass. If true, it would be one of the clearest examples of an intermediate black hole. Another intriguing case comes from observing tidal disruption events, where a star gets too close to a black hole and is torn apart. The pattern of light from these events can sometimes suggest the size of the black hole involved, and a few have hinted at black holes in this middle range. If intermediate black holes truly exist in large numbers, they may be the stepping stones between the death of massive stars and the birth of supermassive black holes. Over billions of years, they could grow by merging with other black holes, swallowing stars, or pulling in clouds of gas. Given enough time and enough matter, they could become the giants that anchor galaxies. It is possible that these middleweights were far more common in the early universe. Back then, the first generation of stars was massive, unstable, and short-lived. Their deaths may have produced black holes larger than most stellar ones we see today. Over time, many of these might have merged or fallen into larger black holes, leaving only a few survivors scattered across the universe. To imagine one, picture a black hole perhaps 1,000 times the mass of our Sun, quietly resting in the center of a star cluster far from the galaxy's center. It feeds rarely, perhaps only when a stray star wanders too close. Most of the time, it is silent, its presence known only by the way it subtly tugs on the orbits of the stars around it. No blinding light, no roaring jets, just the quiet, invisible weight of its gravity. The mystery of intermediate black holes is a reminder that we do not yet see the universe in its full detail. We know about the smallest and the largest, but there is still a missing chapter in between. Each clue we find brings us closer to understanding how black holes grow, evolve, and shape the galaxies around them. Somewhere out there, perhaps in a distant globular cluster or hidden in the faint heart of a dwarf galaxy, an intermediate black hole may be waiting for us to discover it. And when we do, we may finally understand not only how the giants are born, but also the quiet, ancient role these middleweights have played in the story of the cosmos. Far beyond the quiet star clusters and the drifting rogue travelers, at the very centers of galaxies, lie the true giants, supermassive black holes. These are the largest black holes known, containing millions to billions of times the mass of our Sun compared to them. The stellar mass and intermediate black holes are like pebbles beside mountains. Supermassive black holes are not scattered randomly throughout the universe. Every large galaxy we've studied, including our own Milky Way, seems to have one at its core. The one at the heart of our galaxy, known as Sagittarius A*, is about 4 million times the mass of the Sun, yet small enough to fit inside the orbit of Mercury. That balance of size and density is almost beyond imagining. What makes these giants so fascinating is that we do not yet know exactly how they formed. Some theories suggest they began as smaller black holes in the early universe and grew over billions of years by swallowing stars, gas, and other black holes. Others imagine that they might have formed directly from the collapse of huge clouds of gas, skipping the smaller stages entirely. Whatever their origins, once they exist, they have an extraordinary influence over their surroundings. The gravity of a supermassive black hole is so intense that it shapes the motion of stars for thousands of light-years around it. The innermost regions of a galaxy are arranged and stabilized by its presence, almost as if the black hole acts as a gravitational anchor holding everything in place. Yet, despite their power, most supermassive black holes are quiet most of the time. They do not constantly feed. When they do, the process can transform them into some of the brightest objects in the universe. Gas and dust spiral inward, forming massive accretion disks that heat up and glow. Jets of particles can burst from their poles, stretching far beyond the galaxy itself. When this happens, the galaxy becomes what astronomers call an active galactic nucleus, or AGN. Some of the brightest AGNs are called quasars, capable of outshining all the stars in their host galaxy combined. Imagine drifting near the center of a galaxy where its supermassive black hole is feeding. The accretion disk could be vast, swirling with energy, glowing in fierce whites and blues at the center and fading to deep reds at the edges. The jets would pierce the darkness like luminous spears, visible for millions of light-years. Around all of this, the stars of the inner galaxy would circle at incredible speeds, drawn ever closer to the heart of the gravitational well. And yet, not all supermassive black holes are so active. Sagittarius A*, for example, is currently quiet. It feeds only occasionally, sometimes on a stray cloud of gas or a star that wanders too near. For the most part, it waits silently, a patient giant at the center of the Milky Way. The quiet ones are harder to study, but they are no less powerful. Supermassive black holes also play a role in the life cycle of galaxies. When they feed, the energy they release can push gas out of the galactic center, slowing the formation of new stars. This feedback can shape the evolution of the entire galaxy. Without their influence, the distribution of stars and gas in the universe might look very different. The largest supermassive black holes discovered so far are almost beyond comprehension. Some have masses over 10 billion times that of the Sun. One in the galaxy TON 618 is estimated to be about 66 billion times the Sun's mass. If placed in our solar system, its event horizon would stretch far beyond the orbit of Pluto. To be near one is to witness the scale of the universe in its most extreme form. Time itself moves differently here. For a distant observer, objects falling toward the event horizon appear to slow down, their light stretched into red until it fades from view. Inside, for the matter crossing the horizon, there is no turning back. The journey ends at the singularity, a place hidden from the rest of the universe forever. If you could float safely in orbit around a supermassive black hole, the view would be both breathtaking and unsettling. The sky would be dominated by the warped glow of the accretion disk, the stars bent and distorted by gravitational lensing. Jets would cut across the darkness, and behind them, the galaxy's spiral arms would shine faintly in the distance. Supermassive black holes are the giants that rule the galactic stage. They are both destroyers and creators, shaping the galaxies that orbit them, regulating the birth of new stars, and anchoring the vast structures of the universe. Without them, the cosmic architecture we see today might never have formed. In their silent patience or their blazing hunger, these giants remind us that the most powerful forces in the universe can exist for billions of years, holding their place at the heart of everything. And somewhere, deep in their gravity, lies the mystery of how the universe organizes itself on its grandest scales. Every galaxy has a center, but it is not always the same kind of center we might imagine. On Earth, we think of a city with its tallest buildings at the heart, roads stretching outward in every direction. In space, galaxies have something far more powerful at their core, a supermassive black hole. This giant may be silent for millions of years or blazing with activity, but its presence shapes the entire galaxy around it. At first, it might seem strange that something so small compared to the size of the galaxy could have such an influence. After all, even the largest black hole is tiny when measured against a galaxy spanning hundreds of thousands of light-years. But a supermassive black hole is not like any other object. This gravity is the anchor of the galactic core. Without it, the dense clusters of stars at the center might drift apart over time, and the structure of the galaxy could become less stable. One way to understand why these giants matter is to imagine the center of a galaxy as a great whirlpool. The stars, dust, and gas orbit around the black hole much like water spirals around a drain. Except here, the spiral is stable and lasts for billions of years. The black hole's mass helps keep this motion organized. Without that gravitational center, the inner galaxy might become chaotic, with stars scattering into wider orbits or colliding more often. But their role goes beyond simply holding things together. Supermassive black holes can also control the pace of star formation in a galaxy. When they feed, pulling in gas and dust from their surroundings, they release enormous amounts of energy. This energy does not just vanish. It pushes outward, sometimes driving gas away from the center of the galaxy entirely. Since gas is the raw material for forming new stars, this process can slow or even stop star birth for a time. This might sound destructive, but it is actually part of the galaxy's natural rhythm. If too many stars formed at once, they could use up the gas too quickly, leaving the galaxy with fewer new stars in the future. The black hole's activity, by controlling gas flow, helps spread star formation over billions of years, giving the galaxy a longer life. Some of the most striking examples of this influence come from active galaxies whose central black holes are feeding at a high rate. In these galaxies, powerful jets and winds blow out from the center, carrying energy and material far into the galaxy's outer regions. These jets can stretch for thousands or even millions of light-years, stirring up the interstellar medium and changing the conditions for star birth across the galaxy. Even in quieter times, the gravitational pull of a supermassive black hole can shape the orbits of stars far beyond its immediate surroundings. In the Milky Way, for example, the motion of stars in the central bulge, the thick, rounded region at the galaxy's center, is influenced by Sagittarius A*, our own supermassive black hole. Though we are far from it here in the spiral arms, our Sun and the rest of the solar system still orbit the galactic center, completing one revolution roughly every 230 million years. There's also a cosmic historical connection. Astronomers have found that the mass of a galaxy's central black hole is linked to the mass of the galaxy's bulge. This relationship, known as the M-sigma relation, suggests that galaxies and their central black holes grow together. As the galaxy gathers more stars and gas, the black hole grows as well, and vice versa. They are partners in cosmic evolution, each shaping the other's destiny. In some cases, the black hole's role becomes especially dramatic during galaxy mergers. When two galaxies collide, their central black holes spiral toward each other, eventually merging into an even larger black hole. During this process, enormous amounts of energy are released, and the structure of the new galaxy is reshaped. The merger can trigger bursts of star formation, but eventually, the central black hole's feedback may calm the chaos, restoring order to the galaxy. For billions of years, these massive hearts have been quietly guiding the fate of galaxies. They are not simply consumers, devouring everything in their path, though they can do that too. They are also regulators, balancing creation and destruction, growth and rest. Without them, galaxies might look and behave very differently, perhaps lacking the organized spiral arms and defined shapes we see today. So when we say that a galaxy has a black hole at its heart, it is not just a poetic phrase. It is the truth, and it is a truth that speaks to the deep connection between the smallest scales of space, where atoms swirl into stars, and the largest, where stars swirl into galaxies. In the cosmic dance, the black hole is both the anchor and the conductor, keeping time with the slow rhythm of the universe. For most of their lives, supermassive black holes sit quietly at the hearts of their galaxies, invisible and silent. But every so often, something changes. A cloud of gas, a stream of dust, or even an entire star drifts too close to the giant's gravitational pull. Slowly at first, then more quickly, the material begins to spiral inward. And then the galaxy's heart ignites. This is the birth of a quasar, one of the brightest, most energetic objects in the entire universe. The word quasar comes from quasi-stellar radio source, a name given in the 1960s when astronomers first spotted these brilliant points of light in the sky. At first, they looked like ordinary stars through a telescope, but their spectra, the patterns of light split into different wavelengths, told a different story. They were much farther away than stars in our galaxy, and they were releasing hundreds of times more energy than the entire Milky Way. A quasar is powered by a feeding supermassive black hole. As gas and dust spiral into the accretion disk, they heat to millions of degrees. The energy released in this process is so intense that the disk glows across the electromagnetic spectrum, from radio waves to X-rays. In many quasars, this energy also drives powerful jets of charged particles outward at nearly the speed of light. These jets can stretch for millions of light years, shining far beyond the galaxy's borders. If you could watch a quasar up close, from a safe, impossible distance, it would be dazzling. The accretion disk would be a blinding whirl of white and blue light at the center, fading to orange and red at the edges. Around it, magnetic fields would twist and snap, launching streams of particles into space. The jets would cut through the darkness like luminous rivers, straight and unwavering, reaching into the intergalactic medium. Quasars are not just beautiful. They are also important cosmic tools. Because they are so bright, we can see them from incredibly far away, even from the early universe when it was less than 1 billion years old. Studying these distant quasars gives astronomers a way to look back in time and learn about how galaxies and black holes formed in the first place. Some of the most famous quasars are among the most distant objects ever observed. The light from these quasars has traveled for billions of years to reach us, carrying with it information about the young universe. In their light, we can find the fingerprints of early elements, the signatures of intergalactic gas clouds, and clues about how the first massive structures came together. But quasars do not last forever. They are a phase in the life of a galaxy, lasting perhaps 10 million to 100 million years short by cosmic standards. Eventually, the black hole consumes or expels the nearby material, and the accretion disk fades. The jets stop. The once blazing core returns to quiet, waiting for the next opportunity to feed. It's remarkable to think that something so bright, so powerful, and so far-reaching could be powered by something that, at its heart, is invisible. The light we see from quasars is not from the black hole itself, but from the matter falling toward it. In a sense, a quasar is the last brilliant display of energy before that matter disappears forever beyond the event horizon. Quasars also play a role in shaping their host galaxies. The energy they release can push gas out of the central regions, regulating star formation and altering the galaxy's evolution. In some cases, quasars may even help determine the final size and structure of their galaxies. To imagine the scale of a quasar's power, consider this. A single quasar can outshine every star in its galaxy combined, and do so for millions of years. The brightest quasars are hundreds of times more luminous than the entire Milky Way. Yet all of that energy comes from a region no larger than our solar system, a reminder of just how extreme the universe can be. In the grand story of the cosmos, quasars are like brief but spectacular fireworks shows, marking moments when galaxies and their central black holes are at their most active. They light up the darkness across billions of light years, serving as beacons that guide astronomers toward the farthest reaches of time and space. And when they fade, the black holes remain, silent again, but forever changed by their feast. The galaxy, too, will carry the mark of the quasar's activity. In its stars, its gas, and its shape. The light may vanish, but the effects remain, written into the history of the universe itself. Imagine approaching a black hole. From a distance, it might not look like much, just the dark center of a swirling disk of light and energy, or perhaps nothing at all if the black hole is silent. But as you get closer, the space around it begins to change in ways that defy everyday experience. Light bends, stars shift in strange arcs, and the background sky warps as if reflected in an invisible, curved mirror. You are approaching the event horizon, the invisible boundary that marks the edge of a black hole. It is the point of no return. Once anything crosses this boundary, whether it's a particle of dust, a beam of light, or an entire star, it can never escape. The event horizon is not a physical surface like the crust of a planet. It is a region in space where the pull of gravity becomes so strong that escape is impossible, even at the speed of light. Inside, all paths lead inward, toward the singularity at the black hole's center. For an observer watching from far away, the event horizon has some strange properties. If an object falls toward the black hole, it appears to slow down as it gets close to the horizon. Its light is stretched into redder and redder wavelengths, a process called gravitational redshift, until it fades from view entirely. To the distant observer, the object never quite crosses the horizon. It just seems to freeze in place and dim into darkness. But for the object itself, if it could somehow survive the extreme forces, the experience is very different. It would cross the event horizon in a finite amount of time, without noticing anything particularly special at that moment, except perhaps the ever-increasing pull toward the center and the distortion of the outside universe. The size of the event horizon depends on the mass of the black hole. For a stellar mass black hole, it might be only a few kilometers across. For a supermassive black hole, it can span billions of kilometers. In both cases, the horizon is the ultimate boundary, marking the line between the part of the universe we can interact with and the part forever hidden from us. What happens inside the event horizon is one of the great mysteries of physics. General relativity predicts that everything falls toward the singularity, a point of infinite density where the laws of physics as we know them break down. But quantum theory hints that there may be more to the story, perhaps involving the storage or transformation of information in ways we don't yet understand. This is the heart of the famous information paradox. The event horizon is also where some of the most extreme effects of relativity appear. Time itself flows differently here. For someone far away, clocks near the horizon appear to slow down. For someone falling in, the outside universe might seem to speed up, stars and galaxies racing through their life cycles in moments. It is a place where the separation between time and space begins to blur. Scientists have recently managed to image the region just outside the event horizon of a supermassive black hole. The Event Horizon Telescope, a global network of radio observatories, captured the first direct image of the shadow of a black hole in the galaxy M87 in 2019. The image showed a glowing ring of light bent by gravity, surrounding the dark silhouette where the event horizon lies. This was a milestone in our ability to study these mysterious boundaries. Despite its dark reputation, the event horizon is not a wall of destruction in itself. The real danger lies deeper inside, where tidal forces, the stretching and squeezing caused by intense gravity, can tear apart anything that gets too close. Near small black holes, these forces are deadly even before you reach the horizon. Near supermassive black holes, you might cross the horizon without feeling much at all, only to be destroyed later as you approach the singularity. The concept of the event horizon challenges our sense of what is knowable. It is a boundary in nature, not just in practice but in principle. Beyond it, no information can reach us. What happens there is hidden forever, unless new physics, something beyond Einstein's theory, one day reveals a way to understand it. In the quiet darkness of space, the event horizon is invisible, yet it marks one of the most dramatic dividing lines in the universe. Outside, light and life and time continue as usual. Inside, all paths lead to an unknown fate. And between the two lies that perfect, inescapable edge, the place where reality itself bends beyond recognition. Imagine drifting through the blackness of space, your course slowly but surely pulling you toward the heart of a black hole. At first, there is no rush. The pull of gravity grows stronger, but gently, like a tide coming in. You cross through regions where light bends in strange arcs, where the stars behind you appear to smear and stretch across the sky. And then, somewhere in the invisible dark ahead, lies the event horizon, the edge you cannot cross and return. If the black hole is small, just a few times the mass of the sun, the final approach would be anything but gentle. Long before you reach the event horizon, the gravitational pull on your feet would be much stronger than on your head. The difference would stretch your body lengthwise while squeezing it from side to side. This effect has a rather strange name: spaghettification. It is exactly what it sounds like. You would be stretched out like a piece of spaghetti. The closer you get, the more extreme the stretching becomes, until your atoms themselves are torn apart. In a stellar mass black hole, spaghettification would happen so quickly that you might not even have time to realize what's happening. But if you were falling into a supermassive black hole, like the one at the center of our galaxy, your experience would be very different. The tidal forces at the event horizon of such a giant are surprisingly gentle. You could cross the horizon without feeling anything unusual, no stretching, no tearing, no sudden changes. Only after you were deep inside, far closer to the singularity, would the tidal forces grow strong enough to pull you apart. From your perspective, the journey would be smooth and silent. The outside universe, however, would see something very different. To a distant observer, your approach would slow to a crawl as you neared the event horizon. Your image would grow redder and dimmer until it faded completely, as if you had been frozen in place just outside the black hole. In reality, you would have crossed the horizon and continued on your way, forever cut off from the rest of the universe. Inside the event horizon, all paths lead inward. There is no turning back, no direction you can go that will take you away from the singularity. The space around you curves inward in all directions, like a funnel that closes at the bottom. Time itself points toward the singularity, so that moving forward in time is the same as moving closer to it. We do not know exactly what you would encounter as you approached the singularity. According to Einstein's theory of general relativity, the singularity is a point of infinite density and zero volume, where the laws of physics break down. But infinities in physics often mean that our theories are incomplete, that there is some deeper truth waiting to be discovered. Quantum mechanics suggests that something else may happen here, perhaps a state of matter and energy we cannot yet describe, or even a bridge to another part of the universe. Some scientists have speculated about wormholes, hypothetical tunnels through space-time that might connect distant regions of the universe, or even other universes entirely. In some theories, the interior of a black hole might lead to such a tunnel. But whether such structures could exist, and whether anything could survive passing through them, is unknown. What is certain is that the journey inward is one way. Once you begin, there is no stopping, no orbiting, no hovering in place. You are carried forward by the geometry of space and time itself. The light from the outside universe grows dimmer and more distorted, until perhaps only a faint, warped glow remains. And then, there is only the pull toward the center and whatever lies there. If spaghettification sounds violent, it is because black holes are the most extreme environments we know. Yet there is also something deeply peaceful in the idea of falling into one. The motion is inevitable and smooth, with no air resistance, no jolts, no sound. Just the quiet, constant pull of gravity, guiding you toward an unknown fate. And perhaps that is the real mystery. Beyond the event horizon, we cannot see, cannot measure, cannot know for sure what happens. It is a place where the universe draws a curtain, keeping its secrets hidden. Whether the journey ends in destruction, transformation, or something stranger than we can imagine, the truth lies deep inside, beyond reach, beyond rescue, beyond even the concept of outside. In the vast quiet of space, black holes spend most of their time alone, minding their own gravity. But sometimes the universe stages an event so powerful, so extraordinary, that it shakes the very fabric of reality itself. This happens when two black holes meet and merge. A black hole merger is not a quick handshake or a casual passing by. It is the end of a long and slow dance, one that can take millions or even billions of years to complete. Often, it begins when two galaxies collide. Each galaxy's central black hole is drawn toward the center of the newly formed galaxy, and as they drift closer together, their mutual gravity pulls them into an ever-tightening orbit. At first, this orbit might be wide, with the two black holes circling each other from a great distance. But over time, they lose energy, radiating it away in the form of gravitational waves, ripples in spacetime predicted by Albert Einstein a century ago and finally detected in 2015. These waves carry energy away at the speed of light, causing the orbit to shrink bit by bit. As the black holes get closer, the gravitational waves grow stronger. The frequency and intensity of the ripples increase, much like the rising pitch of a whistle as a train approaches. In the final seconds before the collision, the black holes are moving at incredible speeds, half the speed of light or more, and space-time itself is trembling with their power. When they finally touch, they merge into a single, larger black hole. The moment of collision releases more energy in gravitational waves than all the stars in the observable universe emit as light at that instant. And yet, unless you have instruments designed to detect gravitational waves, you would never know it happened. The event is completely silent and invisible to human senses. The newly formed black hole is not instantly calm. It can wobble and oscillate as it settles into a stable shape, sending out a final burst of gravitational waves known as the ring down. Eventually, it becomes still, holding the combined mass of the two original black holes, minus the portion converted into pure energy during the merger. The detection of gravitational waves from such mergers has opened a brand new window into the universe. Telescopes let us see light, but gravitational wave observatories like LIGO and Virgo let us feel the vibrations of spacetime itself. Through these signals, we have learned that black hole mergers are more common than we once thought, happening perhaps every few minutes somewhere in the universe. Not all mergers involve giants in the centers of galaxies. Some happen between smaller, stellar mass black holes left behind by dying stars. Others might involve intermediate mass black holes. In rare cases, supermassive black holes themselves may collide, events so powerful that the resulting gravitational waves could be detected across the entire cosmos. If you could watch a merger from a safe, impossible distance, the sight would be surreal. The two black holes would warp the space around them so severely that the background stars would appear twisted into strange arcs and loops. As they spiraled closer, the distortions would become more intense, the dance more rapid, until they finally became one. In a way, a black hole merger is both an ending and a beginning. It is the end of two separate gravitational identities, but the birth of something new, a single, heavier, and often more powerful black hole. These events help black holes grow over cosmic time, building from smaller seeds into the giants we see in the hearts of galaxies today. Black hole mergers also tell us something profound about the nature of the universe. That spacetime is not a rigid, unchanging stage, but a flexible fabric that can ripple, bend, and carry information across billions of light years. Every time we detect such a ripple, we are catching a whisper from one of the most extreme events imaginable. A whisper that began in a place where light itself cannot escape. For most of human history, our understanding of the universe came only from light. We studied the glow of stars, the reflections from planets, the bursts from distant galaxies. Everything we knew came from photons, particles of light traveling across space to reach our eyes and instruments. But light has limits. It can be blocked, absorbed, or scattered. Some parts of the universe are hidden behind thick clouds of dust and gas. Some events happen in complete darkness, producing no light at all. For these, we needed a new sense, a way to detect the invisible motions of the universe itself. That sense came in the form of gravitational waves. First predicted by Albert Einstein in 1916 as part of his theory of general relativity, gravitational waves are ripples in the very fabric of spacetime. Imagine spacetime as a calm, still pond. When a massive object moves suddenly, like two black holes merging, it sends ripples across that pond. These ripples are gravitational waves, spreading outward at the speed of light, carrying with them the story of the event that created them. For decades, gravitational waves remained only a theoretical prediction. They were so faint, so subtle, that detecting them seemed almost impossible. But in 2015, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, achieved what had once been thought impossible. It detected a tiny, rhythmic stretching and squeezing of space, a change in distance smaller than the width of a proton, caused by the merger of two black holes over 1 billion light-years away. This was not just a technical triumph. It was the opening of a new era in astronomy. For the first time, we could listen to the universe, not just look at it. Gravitational waves carry information that light cannot. They pass through matter without being absorbed or scattered, meaning they can bring us direct news from places light could never escape, like the collision of two black holes or the heart of a neutron star merger. They tell us about the motion and mass of objects, their spin, and the energy released in their final moments. The sound of a gravitational wave, when translated into audio frequencies, is often described as a chirp. As two massive objects spiral toward each other, the waves they produce increase in frequency and amplitude, creating a rising tone that ends abruptly at the moment of collision. It's the faint whisper of a cosmic event, carried across billions of years and detected here on Earth. Our ability to detect these whispers comes from incredible precision. LIGO and its European partner, Virgo, use laser beams traveling along long tunnels to measure changes in distance caused by passing gravitational waves. When a wave stretches space in one direction, it compresses it in the other, and these detectors pick up the difference. It's like measuring the change in distance between two mirrors to within a fraction of an atom. Since that first detection, dozens of gravitational wave events have been recorded. Most involve black hole mergers, but some have come from the collisions of neutron stars, ultradense remnants of massive stars. In 2017, such a collision was detected both in gravitational waves and in light, allowing astronomers to study the event in multiple ways at once. This marked the dawn of multi-messenger astronomy, combining different types of cosmic signals for a fuller picture of the universe. Gravitational waves are also a kind of cosmic archaeology. By detecting them from different distances, we are effectively listening to events that happened at different times in the universe's history. Some of the waves we detect today began their journey billions of years ago, when life on Earth had not yet formed. Others might come from even earlier times, perhaps from the first moments after the Big Bang, if we can develop instruments sensitive enough to hear them. The future of gravitational wave astronomy is full of promise. Plans are underway for space-based detectors like LISA, the Laser Interferometer Space Antenna, which would orbit the Sun and detect waves from supermassive black hole mergers and other slow, massive events. On Earth, upgrades to LIGO, Virgo, and other observatories will make them even more sensitive, allowing us to detect fainter and more distant events. In the grand story of the cosmos, gravitational waves are a new chapter, one we have only just begun to read. They remind us that the universe is not silent, even in its darkest corners. It hums and rings with the echoes of ancient collisions, the slow dance of massive objects, and the sudden, violent transformations that shape galaxies and stars. Every ripple we detect is a message from across time and space, a faint whisper that says, "Something extraordinary happened here, and now you know." For a long time, black holes were thought to be eternal. Once formed, they would remain forever, dark, silent prisons from which nothing could escape. Their only possible fate seemed to be to grow larger as they swallowed more matter and energy. But in the 1970s, a young physicist named Stephen Hawking made a startling discovery. Black holes might not last forever after all. What Hawking realized was that, according to the strange rules of quantum mechanics, black holes could actually lose mass over time by giving off a faint glow. This process, now called Hawking radiation, would eventually cause a black hole to shrink and vanish entirely. To understand why, we have to look at what happens in the empty space around us. Empty space is not truly empty. On the smallest scales, it is alive with activity. Particles and their opposites, called antiparticles, constantly pop into existence in pairs, then quickly collide and disappear again. This constant flicker is part of the quantum fabric of reality. Now imagine this happening near the event horizon of a black hole. A pair of particles forms, but one falls into the black hole while the other escapes. To an outside observer, it looks as if the black hole has emitted a particle. The one that falls in has negative energy relative to the outside universe, which reduces the black hole's total mass ever so slightly. Over unimaginable lengths of time, this steady trickle of energy could cause the black hole to shrink. The smaller the black hole becomes, the faster it radiates, until in its final moments it releases a burst of energy and disappears completely. For a black hole the size of a star, this process is incredibly slow, far longer than the current age of the universe. Such a black hole could take many trillions of years to evaporate. But for tiny black holes, perhaps formed in the early universe, Hawking radiation could be significant, leading them to vanish more quickly. Hawking's idea was revolutionary because it connected three great areas of physics: general relativity, which describes gravity and space-time, quantum mechanics, which governs the smallest particles, and thermodynamics, the study of heat and energy. Black holes, once thought to be purely gravitational objects, suddenly had a temperature and could obey the laws of heat flow. The discovery also deepened the mystery of what happens to information in a black hole. If a black hole evaporates completely, what happens to the information about everything that fell inside? Does it disappear, violating the rules of quantum mechanics? Or is it somehow encoded in the Hawking radiation? This question, the black hole information paradox, remains one of the most fascinating unsolved problems in physics. Hawking radiation is far too faint to detect from any black hole we know of today. Even the supermassive black hole at the center of the Milky Way would emit radiation much weaker than the background glow of the universe itself. But its theoretical existence has inspired decades of research, and physicists are still exploring ways to test the idea, perhaps by recreating similar conditions in laboratories using analog systems. If Hawking was right, the ultimate fate of every black hole is to fade away. Over the vast, cold future of the universe, stars will burn out, galaxies will dim, and the last black holes will slowly evaporate into nothingness, leaving behind only the faintest whispers of their presence. It's a strange thought. The most powerful gravitational traps in the universe, capable of swallowing stars whole, may end not in a violent explosion, but in a slow, silent fade into emptiness. For all we have learned about black holes, they remain among the most mysterious objects in the universe. We have imaged their shadows, detected their collisions, and measured their influence on nearby stars and gas. We have even begun to listen to their mergers through gravitational waves. And yet, when it comes to the deepest truths about black holes, our knowledge is still only scratching the surface. The first great mystery is the singularity itself, the point at the center of a black hole where, according to general relativity, density becomes infinite and the known laws of physics break down. We cannot see it, measure it directly, or send a signal from it. It exists only in our equations, and those equations tell us that we need something beyond Einstein's theory, a true theory of quantum gravity, to understand what happens there. The second mystery concerns information. When matter falls into a black hole, is the information about its physical state truly lost forever? Quantum mechanics says information cannot be destroyed, but black holes seem to defy this rule. Stephen Hawking's idea of Hawking radiation brought the problem into sharp focus. If a black hole evaporates, where does the information go? Some theories suggest it might be hidden in subtle patterns within the radiation itself, or stored on the event horizon in a kind of holographic form. Others hint that space and time themselves might be more complex than we think. Another question is how supermassive black holes form so quickly. Observations show that some of these giants existed less than 1 billion years after the Big Bang. Did they grow from the collapse of enormous early stars? Did smaller black holes merge together rapidly in dense regions? Or could there be a different process altogether, one we have yet to imagine? The role of black holes in galaxy evolution is also still being explored. We know that their activity, especially during quasar phases, can blow gas out of galaxies and slow down star formation. But how exactly do black holes and galaxies influence each other's growth over billions of years? Are black holes the regulators of galaxy life, or simply powerful byproducts of it? On the experimental side, the future of black hole research is bright. The Event Horizon Telescope continues to refine its images, with the goal of capturing even more detailed views of the environment near event horizons. Planned space-based gravitational wave detectors like LISA will be able to detect the slow, massive mergers of supermassive black holes across the universe. New X-ray, infrared, and radio telescopes will allow us to peer through cosmic dust and gas to watch black holes feeding in real time. There are also exciting possibilities for testing physics itself. Black holes push the laws of nature to their limits, making them natural laboratories for studying extreme gravity, high-energy particle physics, and the structure of space-time. If our observations ever deviate from what general relativity predicts, it could point the way toward new physics. And then there are the more speculative ideas, black holes as possible gateways to other universes, or as storage for the building blocks of reality itself. These ideas are far from proven, but they remind us of something essential. Black holes challenge us to imagine beyond what we currently know. Perhaps the most humbling truth is that black holes are not rare. They are scattered across our galaxy, millions of them quietly orbiting among the stars, with countless more in the universe beyond. They are both dangerous and essential engines of change, markers of cosmic history, and windows into the deepest laws of nature. We may never be able to travel to one or to send a probe inside to report back. But through careful observation, creative theory, and the relentless curiosity that drives science, we will continue to learn more about these mysterious giants. The future of black hole research is a journey, not toward the center of a galaxy, but toward the center of knowledge itself. And the closer we get, the more we realize. The horizon is not an ending, but an invitation to look deeper. And so, our journey through the realm of black holes comes to an end. We have floated past the smallest of them, born from the death of massive stars, and we have gazed in awe at the giants that sit at the hearts of galaxies, shaping their fates. We have approached the event horizon, that invisible edge where time and space twist into new shapes, and we have wondered about the singularity, the mystery at the center that defies our understanding. We have listened to the universe's faint whispers in the form of gravitational waves, felt the silent violence of black hole mergers, and imagined the slow fading of these cosmic titans through Hawking radiation. We have considered the question science has yet to answer, and the possibilities that lie ahead for the researchers of tomorrow. Black holes are not just traps for light. They are storytellers, marking the deaths of stars, the births of new galaxies, and the evolution of the cosmos itself. They remind us that the universe is both violent and beautiful, both destructive and creative, both mysterious and deeply connected. As we drift away now, leaving the darkness behind, the stars begin to reappear. The sky opens again into a calm sea of light. The pull of the black hole fades, and we are once more free to roam the gentle currents of the galaxy. Somewhere, far behind us, the black hole remains, silent, patient, and eternal, or perhaps slowly evaporating into the void. Close your eyes and let that thought carry you, not into fear, but into wonder. Because in a universe so vast, every mystery is an invitation, and every horizon is just the beginning of another journey.